Okay, let's look at the tennis problem. I didn't, the problem itself is fairly wordy, so I did not put the whole thing on this sheet here, but please review it on your worksheet. And I like this problem because it contains kind of a combination of one-dimensional motion and two-dimensional motion. So the information that we're given here is, so note the given information. Just highlight that. The initial velocity v naught prime, the angle, so initial speed really, the angle of launch theta, we're given d, and what d is the opponent's initial position when the ball is first hit. T prime, which essentially is the opponent's reaction time, and then H, which is the height above launch point from which the opponent returns the ball. So basically, you can, if you play tennis, you can think about the fact that your opponent is up near the net, and so you're gonna like lob it all the way to the back of the court so that she has to run all the way back there to return it, and she's gonna return it with an overhead, say. So she's hitting it back at a higher point than you launched it. So kind of, wrap your mind around what's going on there. And what we're trying to find here is what does her average minimum speed have to be, or her minimum average speed have to be in order for her to get back there in time. And we just are going to care about her average speed because obviously she's going to be at rest. She's going to then accelerate to some speed, and then she's going to accelerate again back to rest to hit the ball. So we don't want to have to worry about all that with her motion. Our focus really here is the projectile motion. Okay. So draw yourself always a diagram so you can make sure that things make sense to you. Let's go ahead and put a coordinate system on this, as we always have to do. Coordinate system consists of an origin and a sign convention. So I'm going to go ahead and put the origin at the launch point. You don't have to do that. You can put it wherever you want, but I kind of tend to like it at the launch point. That feels somewhat intuitive to me. So I'll put that there. And then as far as sign convention, I'm going to go ahead and go with upward positive for Y and then rightward positive for X here. I think that makes sense for this particular problem. All of my X quantities, displacement, initial velocity are rightward directed. And then I have initial velocity and displacement in the Y are upward directed. So 2 out of 3 there. So I'm going to go ahead and choose upward. I also want to label something else. Let's think about the fact that well, we're another quantity we're interested in is the how far the opponent has to run. So I'm gonna just like grab that quantity, say I'll call it S, right? Just so I have something to work with. So basically her average speed is going to be equal to the distance she has to run there, S, divided by the time she has to run it in. So I just kind of want to parse that out before we get started because we should always keep our eye on what it is we're trying to find. So her average speed, and I'll just call that V bar here for the that's opponent. I don't want to use an O there because that'll look like V naught. So I'll just call this V bar, the thing we're trying to find. So her average speed is going to be the distance she has to run, which is S, over the time she has to run it in. And that's going to be the time of flight for the ball minus her reaction time, T prime. So in other words, when you hit the ball, there's some, calculation that has to take place, right, in the person's brain. It happens real fast. Our brains are super good at this. But there is reaction time. Reaction time is real. So we don't need to only consider the time it takes for her to get back there, but the reaction time as well. And that's described in the problem. So this is, I just laid this out right now because this is like where we're going, right? We know that we have to separate our X and our Y, that they're totally independent of one another. So let's do that now. Let's go ahead and take that initial velocity vector, just given here as V naught prime. Here's theta, and let's go ahead and break that up into its components. I'll switch color and do that. So I've got, here's my x component. Remember, I'm sorry, here's my y component, and I'm going to remind us that positive y is upward. And then here's my x component. And I'm going to remind us that positive x is rightward. So my x component is going to be v naught prime cosine theta, and my y component is going to be, I'm going to write this sideways to give myself space, v naught prime sine theta. And I'm just using SOHCAHTOA there to figure out which side of the triangle I care about. Okay, cool. So we can see that in order to solve this, we need a couple things. We need to be able to figure out what that S value is, and then we need to be able to figure out what the time of flight is. Two things. So we're going to have to um, investigate both the X and Y motion. When I'm interested in time, I usually investigate the vertical motion in order to find time because that generally is limited by the vertical motion. So I'm going to start there and we'll just look at this equation here. Y final equals Y initial plus V naught YT plus 1/2 AYT squared. So here's my general equation. Remember, we always start with our general equation. And from there, I'm going to fit it to my problem. So my Y final here, let's kind of go through this and think about what are the quantities that we know about Y, right? So my Y motion, what do I know? I know that Y naught is equal to 0 because I have called my origin the launch point. I know that Y final is equal to H. That's positive since I have upward positive, and H is above the Y equals 0 point. Um, V naught Y is equal to, that's directed upward, so that's positive. It's equal to V naught prime sine theta. And AY, the acceleration in the Y, that's directed downward, which is negative in the sign convention, is equal to negative G. All right, so here are the things that we know about the Y motion. And we're going to use those in order to help inform how we use our general equation. I'm using position with respect to time. So I fill in H for Y final, 0 for Y initial, um, V naught prime sine theta for V naught Y, and then minus 1/2 gt squared here. Again, that negative sign is because the acceleration is downward directed, so negative. I would use quadratic formula here, and then in using quadratic formula, I'm going to get two values. So let's just look at that real quick because I want to talk that through. So we would get here v naught prime sine theta plus or minus square root v naught prime squared sine squared theta minus 4 g over 2 h. That's all over 2 times g over 2. Okay, so I want to just draw your attention for a moment to this deciding here about the plus or minus. So this is cool. It's symbolic, so you can kind of see how things are going to work out with this problem. But what you'll notice is that we get two solutions, and they're both physical solutions. They're both positive solutions. You don't get like a negative time. And think for a second about why that would be. Why would that be? How would that be physical? And hopefully what you came to is that they're actually, what we're putting into the equation is we're asking the equation, and I mean this equation right here, right? We're asking it, when is y equal to h? When is y equal to h? And the equation is telling us, oh, y is equal to h 2 times. One time on its way up, so like here, and the next time on its way down, right? So y is equal to h twice. So of course it makes sense that there should be two physical answers to this problem. We know though that we need the greater of the two. We only care about the second time that it goes through y equals h. So we're going to choose the greater of the two. So we'll choose the positive sign to obtain the greater time there. And when we do that, what we end up with is t is equal to v naught prime sine theta over g plus v naught prime squared, sine squared theta minus 2gh over g. Okay, so I mean, you can like make that a little cuter as far as simplifying that, but that's not our focus here. So during that time, right? So now we have the time of flight, so good for us. And now we can figure out how far, we need to find how far the ball traveled in that time so that we can figure out what s is, right? So now we need to look at the x motion and substitute this time in. So if I look at the x motion, I'm going to change up my color here actually. So if I'm going to look at the x motion, um, I can look at x final equals x initial plus v naught xt plus 1/2 a sub x t squared. And I'm going to apply, this is my general equation, right? Now I'm going to apply my particular x information to that. And what do I know about the x motion? Let's figure that out right here. X naught is equal to 0 because of where we put the origin. X final is equal to, we don't know, we're trying to find that, right? We're trying to figure that out right now. V naught x is equal to V naught prime cosine theta, and a sub x is equal to 0. This is a projectile problem. There's no acceleration in the horizontal. So, all right, so tends to be simpler, right? Since there's no acceleration there. So x final is what I'm trying to find, right? X final is equal to 0 plus V naught prime cosine theta times t plus 0. Okay, so that's super handy. Then in order to express my x final here, what I need to do is multiply v naught prime cosine theta times that big expression for t that we figured out. Yeah, and that'll give me the x, my x final that I need. So I'm going to do that on the next page just so I can come up with a little bit more space. X final is equal to v naught prime cosine theta multiplied here. I'll do this over g multiplied by v naught prime sine theta plus root v naught prime squared sine squared theta minus 2gh. Okay, so that's my x final. Now the distance that she has to run though is going to be x minus d, which is this distance s here that we came up with on the first page. So let me write that out then. S is equal to x final minus d. Let's go back again and remember why that's true. So x final is the whole distance, right? This whole thing here is x final, that whole thing. So x final minus d gives us the s, which is the distance she needs to run. And she needs to run in a time of t minus t prime. So her average speed, again, if I'm just going to write out the expression for that, is going to be x final minus d over t minus t prime. Okay, so we can write that out in terms of our equation. So x final is this whole expression up here I'm going to change my color just to make it a little more visible here. Um, okay. I know, silence. It takes me a minute to write all this out. So there's my X final. I'm going to take this quantity here, subtract D. That gives me my numerator, right? And then in the denominator, it's T minus T prime. So T I'm getting from the page before. That's all over G. That's my T minus T prime. And I just realized that I should have used a lowercase h right here. That's important. In science, we care about the difference between uppercase and lowercase letters. Oh, and I did the same thing up here. They could be in a particular problem that uppercase and lowercase h's could be completely different quantities. So I'm trying to be good about that. Okay. Yeah. So, I mean, obviously, you can do a little algebraic simplification and stuff. Again, I don't put a lot of focus on that because I mean, that's not our physics is not that, right? As long as the physics is right, then we're good, and we can always do a little manipulation of the algebra later. So this is the final one. If this feels like, oh my gosh, there's all these symbols and all these expressions, then welcome to physics. And this shouldn't scare you. Algebra shouldn't scare you. That's one of the reasons that calculus is a prerequisite for this class. Sometimes students wonder why it is, because we don't use a ton of calculus in here. The biggest reason is that you are expected to be really fluent in your algebra in this class. And generally, getting through calculus means that you have pretty good algebra skills. You don't have to think about it too hard and you're fairly fluent. Okay, so that's the tennis problem.